So now what we're going to do is track the actual distance of a cannonball because we know on Earth we have gravity, and gravity will bring that cannonball back to the ground. So if we look at what we put without gravity and go back here to our original table, what we're going to do is plot the other table down below it. So again, here is the actual data. And then here is our theoretical data that I'm going to copy and put back in. So at 0 seconds, we were at 10. Then if I go back here, we were at 416. At 1 second. At 2 seconds, if I go back, we're at 822. Then for 3 seconds, going back and comparing, it was 1228. And then here, 1634. And then lastly, 2040. So if I compared these and made two observations, well, one thing that I notice is that the real distance is always below that linear distance. So the actual distance is below the linear one. And then one thing that I notice is that both have the same y-intercept of 0, 10, or both we can just say start at 10 feet. So what we're going to do now is just plot both graphs, and I'm going to start here with the first equation and put that in blue. So 10 feet would be way down here. Then 400 is going to be right around here. 758, probably in between, halfway in between, about right there. 1084 for 3 seconds. So again, it's going to be pretty close to 1,000. For 4 seconds, 1,378. So I'm just going to estimate that to be about right there. And then for 5 seconds, it's at 1640. So what I want you to notice is there's a little curving. So the cannonball looks like it's going to eventually go back down to the ground and follow a parabola. So here, for our second graph, I'm going to put that in black. So it's going to start at 10, then be at about 416, then 822, then 1228, 1634, and then 2040. And if you notice, the second graph is linear. So this is linear. This is a parabola. So to answer this question, how are the two graphs alike? Both have the same y-intercept. And then one graph is linear, and then this graph is going to be quadratic. Now, we need to write an equation for the actual distance. So what we're going to do is just compare the distances between them. So I want you to notice this one, they both started at the same point. But to move from the predicted to the actual, we subtracted 16 feet. Then if I look here and I find the difference here and go 822 minus 758, that gives me 64. Now, if you remember, I can put that as this one. Remember, we're minusing 16, and that would be times 1. And then 64, if you remember that, can't we put that as minus 16? So if I take 64 and then divide that by 16, that would be 4. But I can write that as 2 squared. So I can put that as minus 16 times 2 to the second power. And similarly, it looks like for this one, we might do negative 16 times 3 to the second power, then negative 16 times 4 to the second power, and then minus 16 times 5 to the second power. So let's look at that difference. So 1228 minus 1084 gives us a difference of minus 144, which again, we can divide by 16. So write that as minus 16. And instead of writing times 9, we can write that as times 3 squared. And you notice, in general, we took our value here. So what we did, our distance started with our initial 10 feet. And then we added that linear distance on. And if you remember, that was 406 times the number of seconds. So I'm going to put plus 406 times t. And then what we did was we subtracted off 16 times t squared. Now, this is an interesting formula. So right here, this 10 represents our initial height. This 406t is our vertical velocity. And this minus 16t squared is the effect of gravity bringing it down.